Please welcome Adrian, Șendroiu, and Vladimir Diaconescu from Bitdefender. They will be presenting talk hide and seek about a peer-to-peer botnet.
Good morning, everyone. We're here to talk about a new botnet which we found in January this year. It's very unique, and I'm sure you're going to agree with me. This talk is going to be a bit more technical for two reasons. One being, well, we find it very interesting on how it behaves, and the second being, we know how it works. We don't know actually why, in the sense that we have no idea what the offer's intention is to do with this. So if anyone has any idea, or if the offer is in this room, please tell us what are you doing and let us live our lives, okay? Okay. So a bit of context. The pointer doesn't seem to be working at this point. I think. Yep. All right. Small hiccup. So we've seen in the previous talk the state of the art in IoT botnets, of course, is Mirai and all of its variants. I'll just briefly walk you through it just so we're on the same page and give you a bit of context and perspective moving forward. So we usually have a central C2 server, and we may also have some separate machines used for just for infecting or for to which bots report newly found victims, which will then be infected. Usually these are all on the same server. The main takeaway from this slide is that regardless of implementation variants and details, they all share the same purpose, and that is denial of service. So what is hide and seek in this landscape? It's a peer-to-peer IoT botnet. It's not the first of its kind. We've also seen Hajime, although Hajime uses BitTorrent as its peer-to-peer protocol. Excuse me. Hide and seek uses a custom peer-to-peer protocol written from scratch. It's also modular. What we mean by that is that it can be updated in real time. It keeps a cache, not necessarily a cache, but a configuration which contains all of its known exploits, and this configuration can be updated on the fly from nearby neighbors. It also supports file sharing, so the malware has access to the local file system, and it caches any data that it founds that is specified through a runtime argument, and this data can be requested via hashes. I've mentioned the update system. The bot can be updated only with a valid signature. So each bot has a hard-coded ECDCA public key. Only the offer has the private key, so no arbitrary peer can update the entire network. One other interesting thing is that the bot itself can be replaced, so it can run arbitrary executables, receive arbitrary executables, and run them. And also, from all that we've seen and analyzed, it has no denial of service capabilities. So that's why we're really befuddled on what on earth it's doing. Okay, as any bot worth its salt, it features two main components, one being the scanner component. Each bot randomly generates an IP address and a port from its list of known ports, meaning ports with which it can interact with. It will then attempt to connect to said IPM port. If it gets a reply, then it will go through the ropes and attempt to exploit the found device. And of course, the peer-to-peer protocol itself. This is used, as I've said, for file exchange, for updates, for propagating throughout the network, for exchanging peers, updating peers, and so on. So as I've said, the scanning process goes a bit like this. Each bot generates a random IP address and then picks a port from its known its list of known ports. Initially, when we found it, it started with the first two bullets, Telnet and HTTP. ADB is the latest addition. So at this point, hide and seek is capable of hijacking ADB devices exposed over the internet and also some other ports. So let's take a look at an example. We have our potential victim here, and of course we have a bot somewhere out in the internet. At some point, this bot will generate the victim's IP address and select, let's say, Telnet. If the victim has Telnet open, then the bot will send a raw SYN to the victim. If the victim replies, then the bot will initiate a regular TCP connection. It will then ask for a login prompt. If the victim supplies such a prompt, then it goes through a dictionary of hard-coded usernames and passwords to attempt to log into the actual device. If it manages to get a shell, that means getting a valid username and password, then it proceeds to probe around the device. So it will attempt to find the architecture and various other information such as memory, file system, and so on. And also it will probe around for tools which it will use to get the actual payload, such as this. So it will try to see if wget is on the system, if curl, if base64. If none of these are found, then the last resort is to actually echo the bytes into the file and make it runnable and run it. Okay, so at this point the malware is copied onto the victim. And how does it get run? It has a series of command line arguments, one being a list of initial starting peers. So hide and seek went through a few changes. It started out with a list of 14 hard-coded peers into each bot. Then in a successive update, it discarded those peers. So the only method through which peers were propagated was by this command line argument, and nowadays it has over 100 hard-coded peers into the binary, so it went through a lot of changes. Moving forward, a kill port. This means that the similar to other botnets, Mirai also does this. It looks through /proc for processes which listen on said port and terminates these processes. This is to eliminate any competition and any potential competition which will attempt to connect to this device. So it effectively shuts down Telnet. Also, another interesting argument is a listening port. This is a UDP port through which the device is identified inside the network, in the botnet itself. This argument is optional. If it's missing, then the bot will generate a IP at random, a port at random through which it will advertise itself in the network. Lastly, also an optional argument are additional scan targets. So as I've said, the bot generates IPs at random. It can also receive specific IPs to be scanned at some point. Okay. Go ahead.
Okay, so now we'll move on to the peer-to-peer protocol. So as my colleague explained, it's a custom protocol over UDP. And there are two topics that I want to cover. One is the data structures involved in this protocol, and the other one are the messages that are going to be exchanged by the peers. First data structure is very simple. It's a peer table, so basically every peer in the network will maintain a list of IPs and ports of the other peers that it knows about. As my colleague said, those entries come either from the command line, from hard-coded from the binary, but most of them are dynamically obtained from the network itself. And another bunch of data structures are those two. We call them config cache and data cache. And they are in fact just some hash tables, some mappings. The config cache, the one on the left, is a mapping between a so-called payload ID and a hash value. And the other one, the data cache, is a mapping between a hash value and some actual data blob. The entries in those structures, again, they come from the peer-to-peer network itself. They are initially empty. What is the usage of those two structures? Well, if we go back to the scanning process, so here we have the scenario where we have this infected machine, the one in red, that is trying to exploit another vulnerable machine, and it has just obtained a shell on this machine. What follows next is a system identification stage, where the architecture of the system is trying to be determined by using, for example, this kind of command, proxy info, from where it might get an answer like this, telling it that it's an ARM system. And now the question is what to actually download on this victim system. Normally, in other botnets like Mirai, a binary would be downloaded from somewhere, but this here, of course, cannot be done because we're talking about a decentralized architecture, and so there's no such thing as a central server. And this is where those two structures come in handy. Basically, the bot will know about a correspondence between an architecture like ARM and the payload ID. For example, ARM is payload ID 15, so it's going to look up this value into the first structure, into the config cache. It's going to find out some hash value and look it up into the second data structure, and finally find some actual data, which is the data that is going to be actually injected into the system, which you can see it's an actual F binary, it's an executable file. And not only this, but it's actually the hide-and-seek sample itself compiled for this particular architecture. So you see, in fact, what happens is that every peer in the network, every infected machine can act as a download server, and it keeps in memory a list of all the samples compiled for each major architecture like ARM, MIPS, x86, and so on. Of course, if you find this sample running and you dump its memory, you can very easily get all those samples. And again, the fact that all those entries come from the peer-to-peer network makes it quite flexible, so the author can very easily change those payloads by pushing the modifications throughout the peer-to-peer network. Okay, now I'm going to move on to the protocol itself, and I'm going to present 3 scenarios in which we're going to see what kind of messages are going to be exchanged by the peers, and we're going to see what the network is capable of achieving. First of all, the message format is this one presented here, quite simple, just 1 byte to identify the message type, followed by the rest of the message, depending on the message type. The first scenario is how this config cache is updated. As I've said before, it is empty in the beginning, and it must get those entries. And this happens like this. So we have this peer in the middle, the one in orange, which, let's say, has just started, so its structure is empty, and it's going to send this message throughout the network, lowercase h, together with the value 0. This is to say like oh, my version of this structure is 0, that is empty, so please, anyone else who has a greater version than this, please reply. And this happens, so every peer will send back their own version of the config cache, and our peer in the middle will eventually pick the one with the greatest version as the source from where to download this config cache. And it's going to do this by using another class of messages related to data transfer. What is important to know is that every transfer happens in chunks of 256 bytes. And we have those two messages, chunk request, which includes the chunk index. In this case, it's 0, it means the first chunk. And the chunk reply, which has the actual data. After the transfer is complete, the signature check step follows, as my colleague explained. Why is that? You see that this config cache is quite an important structure because every infection process starts with a lookup in this structure, so whoever controls this can actually control what payloads are going to be injected. So probably this is why the author decided to require this to be digitally signed. And of course, those two messages, chunk request and chunk reply, are used for any kind of data transfer, not only for this, but for the other structure as well. So all these binary blobs are also transferred in the same way, minus the digital signature check step. A second scenario is related to peer management. As I've said before, most of the peers are obtained from the network itself. So this is how a peer will broadcast this peer request message. Upon receiving this, the other peers will pick an entry from their own table and send it back. And this peer, upon receiving all those replies, will insert those IPs and ports into its own peer table. So this is how it ensures that everyone has a consistent view of the peer table. And the last scenario is this one described here. So we have an infected machine that is trying to exploit some other vulnerable device using, for example, this HTTP exploit. But this exploit fails for some reason. So what might happen is this peer will use this message to report the IP and the port of this target device to another peer in the network. And when this other peer will go to the scanning routine, it will also consider this IP besides all the other ones that were randomly generated. This means that this peer will also try to exploit this device as well, hoping that it will succeed in this case. Maybe this peer is running a newer version of the bot that is more capable of exploiting more devices. So to sum up, the botnet that we just presented is a botnet that can spread very efficiently throughout the internet and infect many kinds of IoT systems. It has a decentralized peer-to-peer architecture, and of course the control of this network is still in the hands of the author due to the fact that the most important structure in the botnet needs to be digitally signed in order to be updated. So now let's move on to a little bit of history. So at Bitdefender we've seen over 30 samples of this binary, which kind of suggests that the author is still trying and testing different things. Most of them were code refactoring, minor changes, but some new functionalities were added as well, among which we can mention persistency. So many other botnets like Mirai, they usually delete their own executable file after startup. That means they will not survive after a device reboot. But hide and seek is able to copy itself to the standard location /etc/init.d, and it will copy itself under this name S99 followed by some random characters. Another one is the ability to drop and execute arbitrary binaries, as my colleague explained. Again, those binaries that are dropped come from the peer-to-peer network, and this means only the author can control what exactly is being dropped. And in particular, we've seen a case where a Monero miner was dropped, but it didn't really have that much success, probably because those devices are not really that powerful to be able to mine cryptocurrencies. And of course, we've seen updates responsible for extending the exploit capabilities. The first sample that we've seen had only 2 exploits, I think, some TP-Link and something else, but more were added. Kind of the same idea, some command injection in the HTTP interface of some cameras and routers and so on. But we've also seen some other interesting things. For example, we have these 2 database servers, OrientDB and CouchDB. They also provide an HTTP API, and this API allows code execution under some circumstances, and hide and seek is able to take advantage of this and hijack those devices. And the one that my colleague said about the hijacking the Android via ADB. Okay. Some words about monitoring. This, of course, is quite a challenge because of the decentralized nature of the network. So one place from where we can start is to look at the peers that we found hard-coded in the samples. We gathered all of those, and we're talking about 40 countries, and here's like the top 10. The rest of them have like more 5 or less hits. But of course, there is another way of doing things, which maybe you have figured out by yourselves, and that one is to take advantage of these commands, the peer request and peer reply. So what we can do is we can start from some peers and send this command ourselves, and we get back some IPs and continue the process until we have reached a stable list of peers. And we've done this, and since the beginning we've found around 300,000 peers, 300,000 infected devices with this kind of geographical distribution. What is important to notice here is that even though this number is quite high, if we consider the number of active peers at one moment of time, the number is not that big. For example, if we consider the peers active in the last 24 hours, we only get like 4,000 or 5,000 devices, which one explanation might be that the network is not that stable. It's kind of losing peers over time or something like this. As for conclusions, we believe that there is a new trend emerging in the IoT landscape. Since in the past we've seen bots, malwares like Qbot or Mirai, which were not very complex in themselves, but they were kind of the proof that there is a lot to do in this area, given the existence of all those cheap and insecure and hard to update devices. And now we believe that a new trend is emerging towards more complicated and more complex and more dangerous malware. So we've seen things like Hajime with its complex network over BitTorrent. We've seen Satori and other Mirai variants which are able to also exploit HTTP interfaces of IoT devices. We've seen Reaper, which comes with some exploits embedded as well. We've seen probably the most complex so far VPN filter, which is multi-stage and also is able to exploit many kinds of devices. And we believe that the one that we presented today, hide and seek, is also part of this trend, even though we cannot say for sure what the purpose of this bot is, but the complexity and the decentralized architecture makes it part of this. And since the security of those devices hasn't really improved that much, we believe that this is kind of an interesting research area in the future, and it's an area worthy to keep an eye on for more threats to emerge.